What makes Proxima B interesting is that it's an Earth-like planet orbiting the nearest star to the sun.
This planet is definitely the closest planet to the sun that's not orbiting the sun. This one, though, is different. It's special because it's really our neighbor.
A fascinating planet similar to ours is located in the great expanse of space, just over 4 light-years distant. Like our own planet, this distant relative of Earth is capable of supporting life. This is Proxima B. This Earth-like world has long been a source of fascination, orbiting Proxima Centauri, the star nearest to our sun. We found it via mathematical models rather than by first-hand observation. Recent discoveries from the James Webb Telescope, however, have clarified some remarkable features and added to the enigma. Is there life on this far-off planet? What would such life forms look like if they existed? Now that the James Webb Telescope has published a true image of Proxima B, we can see it much more clearly, and it's not at all what we imagined. What do we currently know then? Let's begin the amazing exploration of today, Earth's second planet, Proxima B. The nearest known star to our solar system, Proxima Centauri, is only 4.24 light-years away. It is a faint red dwarf star that is significantly smaller and colder than our sun, and it is a member of the Alpha Centauri system, a triple star system that also includes Alpha Centauri A and Alpha Centauri B. Because of this, it is difficult to see with the unaided eye. However, Proxima Centauri is now the subject of considerable research due to technological developments in modern astronomy, with telescopes that are sensitive to red and infrared wavelengths providing a closer look. Although the star has been known to us for more than a century, it was first discovered in 1915 by Scottish astronomer Robert Innes. We have only recently started to fully comprehend its potential, especially with regard to its planetary system. How did we end up where we are now then? Let's get started. Astronomers started paying more attention to Proxima Centauri's minute movements in the early 2000s, especially the star's positional wobbles. This might not have seemed like much to the ordinary eye, but the specialists seeing across the galaxy knew exactly what it was. They implied that the star was surrounded by invisible worlds. The motion of the star was being affected by the gravitational pull of circling bodies. As the intensity of these observations increased, it became evident that Proxima B, the planet of Proxima Centauri, may be among the most promising exoplanets in the hunt for extrasolar life. In 2016, astronomers at the European Southern Observatory made the discovery of Proxima B. It's interesting to note that they didn't actually see the planet. Instead, they measured the tiny changes in the star's light spectrum as it moves slightly in response to the gravitational pull of an orbiting planet using the radial velocity approach. The data came from sensitive spectrometers on ground-based telescopes, such as the La Silla telescope in Chile. Although the faintness of Proxima Centauri itself and atmospheric distortions made it challenging. Despite the amazing discovery of Proxima B, we still didn't fully grasp the planet. Only indirect measurements, such as the mass, orbital period, and distance from the star Proxima B could be obtained by Earth-based telescopes. However, these observations were unable to provide comprehensive information about the planet's atmosphere, surface characteristics, or potential for life. Space-based telescopes, the next frontier of exploration, would be useful in this situation. Astronomers had long hoped that new technology would overcome the limitations of ground-based observations. Here comes the James Webb, or James Webb Space Telescope. By avoiding the interference of Earth's atmosphere, James Webb provides a clearer, more detailed view of the exoplanet, enabling astronomers to probe its atmosphere, study its chemical composition, and investigate whether Proxima B might possess the conditions necessary to support life. James Webb's advanced infrared astronomy capabilities have already started to reveal new and startling details about distant exoplanets, including Proxima B. Are we alone then, or is there another individual out there? Let's take our time answering this question. In order to validate or disprove our assumptions, we must first determine what enabled us to gather the evidence and why we should have faith in it. The history of the James Webb Telescope. The spirit of exploration that characterized the 20th century space race is being carried on by the James Webb Space Telescope. Ironically, the excitement around space travel has long since faded. So much so that by the start of the 21st century, mankind would have inhabited the moon and even other planets, according to Stanley Kubrick's 1968 film 2001, A Space Odyssey. Naturally, space fever subsided long before such a project could be completed. However, visionaries persisted. The brightest minds on the planet are working tirelessly to explore every inch of space, which is the last frontier. We got our first space telescope as a result. The Hubble Space Telescope, which was launched on April 24, 1990, transformed our understanding of the cosmos by enabling us to study far-off galaxies, stars, and other celestial bodies with unparalleled clarity. At roughly 547 kilometers from Earth, Hubble's position outside of Earth's atmosphere offered it a distinct edge over ground-based telescopes, enabling high-resolution photographs that showed the universe in all its splendor. It has, of course, produced some of the most important discoveries in contemporary astronomy. Its discovery that the universe is expanding, and expanding faster, was one of its most famous contributions. Our knowledge of the universe was drastically changed by this finding, which was made in the late 1990s. It also helped identify dark energy, the enigmatic component responsible for this fast expansion. In 1995, Hubble also produced the breathtaking Hubble Deep Field photograph, which revealed the grandeur and complexity of the cosmos by capturing hundreds of galaxies in a small area of the sky. In addition to these groundbreaking discoveries, Hubble has played a significant role in establishing the universe's age, offering vital information that points to a universe that is roughly 13.8 billion years old. It has clarified the processes involved in star formation, studied the movements of galaxies, and advanced our knowledge of exoplanet atmospheres. Hubble's observations have improved our understanding of supernovae, black holes, and the complex mechanisms underlying the universe. Hubble, however, has built-in drawbacks. Although it transformed our knowledge of the cosmos, its outdated technology made the construction of a new, more sophisticated observatory necessary. Despite being revolutionary, Hubble's primary observation wavelengths are the ultraviolet, visible, and a tiny fraction of the near-infrared. This makes it difficult for it to see through the dense clouds of dust that frequently block off star-forming regions, far-off galaxies, and the centers of active galactic nuclei. Furthermore, even with sporadic upgrades, parts of Hubble's gear and equipment were outdated, having been built in the early 1990s. Although the telescope's low Earth orbit made servicing flights easier, it was also subject to vibrations that reduced its accuracy. Furthermore, it was challenging to examine the outermost reaches of the universe due to Hubble's comparatively tiny 2.4-meter mirror size, which limited its ability to gather light from dim and distant objects. Because of these constraints, NASA, the European Space Agency, and the Canadian Space Agency worked together to develop the James Webb. It was given its name in honor of James Webb, who oversaw NASA's Apollo program from 1961 to 1968. On December 25, 2021, this upgraded space telescope was eventually launched. James Webb was positioned near the second Lagrange point, or L2, which is about 1.5 million kilometers from Earth, in contrast to Hubble, which circles the planet. Because of its advantageous location, James Webb is able to keep a steady orbit away from the Sun, Earth, and Moon, which lessens interference from their heat and light. James Webb can view the cosmos at L2 without being distorted by Earth's atmosphere or affected by light pollution, which is a problem for ground-based telescopes. Furthermore, James Webb's extremely sensitive infrared instruments depend on the colder atmosphere at L2 to operate properly since they need extremely high cooling. The ability of James Webb to observe in the infrared spectrum is its most remarkable feature. As a result, objects and events that are invisible in the visible spectrum can be seen by the telescope as it looks farther into space and time. Looking at galaxies that are farther away allows us to glimpse them as they were billions of years ago when the cosmos was much younger. Nevertheless, the light from these far-off objects has been stretched to longer wavelengths as a result of the universe's expansion, moving it into the infrared spectrum. Because of this phenomena, which is called redshift, Researching the early cosmos requires examining the infrared part of the spectrum. The faintest and most distant objects from the early eras of cosmic history are among the galaxies whose light James Webb can detect thanks to its infrared capabilities. Revolutionary, huh? But that's not all. The ability of James Webb to investigate exoplanets and their atmospheres is one of its most intriguing features. Through infrared observations of far-off worlds, James Webb is able to identify the chemical composition of their atmospheres, including chemicals that are essential to life as we know it, like as carbon dioxide, methane, and water vapor. James Webb's unparalleled sensitivity will enable it to examine exoplanet atmospheres in hitherto unattainable ways, providing fresh perspectives on the habitability of far-off worlds. Because James Webb can identify biosignatures that may indicate the existence of life outside of our solar system. This capacity marks a major advancement in the hunt for extraterrestrial life. James Webb's enormous 6.5-meter primary mirror, which is made up of 18 hexagonal segments made of ultra-lightweight beryllium and thinly coated in gold to maximize its infrared reflectivity, is the centerpiece of its design. Because of its wide mirror, James Webb is able to gather a lot more light than Hubble, which improves its clarity and detail when observing fainter objects. Additionally, the telescope has a 5-layer sunshield composed of a unique substance called capton that shields it from the sun's heat and maintains the low temperatures required for its equipment. James Webb is able to maintain temperatures as low as -233 degrees Celsius because each layer of the sun shield reflects heat. Its infrared sensors can function at their best in this situation. The near-infrared camera, NIRCam, the near-infrared spectrograph, NIR-SPEC, the mid-infrared instrument, MIRI, and the near-infrared imager and slitless spectrograph, NIRIS, are just a few of the remarkable scientific instruments that are housed on the Space Telescope. From taking pictures of the birth of stars and galaxies to determining the makeup of far-off worlds, each instrument has a specific purpose. For instance, astronomers may examine the earliest galaxies with NIRCam, and they can study distant galaxies and exoplanets in detail thanks to MIRI, which expands James Webb's view into the mid-infrared spectrum. While NIRIS guarantees accurate pointing and makes it possible to analyze exoplanet atmospheres, NIRSPEC enables the telescope to scan numerous objects at once, offering insights into their chemical composition. When combined, these instruments have allowed us to observe objects and phenomena that were previously inaccessible with previously unheard-of clarity. They have also yielded fresh information about the universe's past and the circumstances that could support life elsewhere. Findings from the James Webb Space Telescope. Proxima B is one of the most interesting exoplanets found so far. It is located at 4.24 light-years from Earth. It is a prime candidate for the hunt for extraterrestrial life because it orbits within the habitable zone of Proxima Centauri, the star that is closest to our Sun. The scientific community has been tremendously interested in Proxima B since its discovery in 2016, especially in the area of exoplanet research. Scientists use cutting-edge tools like the James Webb Space Telescope, which launched in December 2021 and is intended to view far-off astronomical objects in infrared wavelengths to gain a better understanding of the planet's environment. This telescope allowed them to get a closer look at exoplanets like Proxima B. The capacity of James Webb to observe the planet's light spectrum using a method known as light spectroscopy marked the beginning of its contribution in research on Proxima B. In order to determine an exoplanet's composition, temperature, and possible habitability, it is necessary to analyze the light that travels through or bounces off of its atmosphere. The presence of water vapor, methane, carbon dioxide, and other gases that could suggest whether the planet is suitable for life are just a few of the minute features in the atmosphere that the telescope can record. In relation to life, we already know that this planet is located in the star's habitable zone, which is an area where the possibility of liquid water on the planet's surface is possible and essential to life as we know it. With a mass roughly 1.7 times that of Earth, Proxima B is somewhat bigger than our planet. Only 7.5 million kilometers separate it from its host star, which it orbits every 11.2 Earth days. To put it in perspective, Earth is roughly 93 million miles, or 146 million kilometers, away from the Sun. The standard unit of measurement for distances within the solar system is 1 astronomical unit. By contrast, the distance between Proxima B and its star, Proxima Centauri, is only roughly 5% of that between Earth and the Sun. Normally, if the star had been anything like our Sun, this would have virtually destroyed the planet. Proxima B, on the other hand, is a red dwarf star that is considerably colder and fainter than the Sun. This implies that Proxima B receives almost the same amount of energy as Earth while being so close to its star, making it, at least in theory, habitable. However, it's not that easy, since one side of the planet is constantly facing the star and the other is always in the dark. The planet is probably tidally locked, which results in sharp temperature differences between the two hemispheres. The planet and its star's gravitational pull causes this phenomena, which results in stark temperature differences between the day and night sides. The night side might be extremely cold, rendering much of the planet inhospitable, whereas the day side would probably be quite hot. A stable atmosphere, on the other hand, would help to mitigate temperature variations by shifting heat from the day side to the night side, which could give hope for habitability. The area that separates the day and night sides may be known as the terminator zone due to this kind of heat circulation. There may be a greater potential for life to flourish here due to the possibly more temperate conditions. Despite these considerations, Proxima B may face difficulties due to its exposure to radiation from its active red dwarf host star, Proxima Centauri. Strong star flares from Proxima Centauri are known to have the potential to deprive the planet of its atmosphere or expose its surface to extreme radiation. The planet's capacity to hold on to its atmosphere and support life over geological timeframes is called into question by this action. However, Proxima B may be able to protect itself from these harsh circumstances if it had a strong atmosphere and a magnetic field. Proxima B's designation as a rocky planet suggests a terrestrial-like structure, perhaps with mountains, valleys, or even oceans. Even though we do not currently have direct evidence on the planet's topography or surface composition, in the event that Proxima B proves to be a gold mine, how might the aliens appear? Rethinking habitability assumptions. The discovery of Proxima B has revolutionized our knowledge of exoplanets, their habitability, and the search for extraterrestrial life. Scientists have re-examined long-held beliefs regarding the possibility of life on planets around red dwarf stars as a result of observations made by the James Webb Space Telescope and other sensors. For many years, it was generally accepted that life was unlikely to exist on planets circling red dwarf stars. About 70% of the stars in the Milky Way are red dwarfs, which are distinguished by their powerful radiation and stellar outbursts. Compared to stars like our Sun, these stars burn at a lower temperature and last a lot longer. Their outbursts were believed to be a major threat to the habitability of planets in the habitable zone, even though their longer lifespan would offer a stable environment for life to evolve. Recent discoveries about Proxima B, however, cast doubt on this presumption. Furthermore, scientists now know that planets like it might exist more frequently than previously thought. In our galaxy, red dwarfs make up the great majority of stars, and many of them have planets orbiting inside their habitable zones. This raises the prospect that the galaxy contains a vast number of Earth-like worlds, many of which might be far closer than previously believed. The discovery of Proxima B has caused a change in the way we hunt for exoplanets that are habitable. This new knowledge puts red dwarf systems at the forefront of future research, whereas the majority of the previous attention was on sun-like stars. Astronomers may find that habitable planets are significantly more numerous than previously thought if they are able to identify additional red dwarf stars and conduct more thorough studies of their planets. It has significant ramifications for our comprehension of life in the universe if Proxima B is home to life, whether it be microbial or more complex. As a result, it is a primary area of study for astronomers, both now and in the future. Proxima B has emerged as a key location for upcoming space research because to its close vicinity. Although sending probes or humans to such far-off exoplanets is now beyond the capabilities of present technology, space technology improvements indicate that expeditions to Proxima B are feasible. Reaching Proxima B during a human lifetime might eventually be possible with the development of next-generation propulsion technologies like nuclear fusion propulsion or solar sails. What can we anticipate finding there, though? We can put Proxima B's possible habitability in context by contrasting it with Earth's extremophiles in the beginnings of life on our planet. Because Proxima B is tidally locked, one side of the planet is always facing its host star and the other is always dark. As a result, the two hemispheres' temperatures differ greatly. The dark side might drop to freezing temperatures, while the side facing Proxima Centauri might reach temperatures as high as 400 degrees Celsius or 752 degrees Fahrenheit. In spite of this, the planet might still be able to sustain life in some circumstances, particularly if its atmosphere is sufficiently dense to control temperature and keep harsh environments from stifling life. Extremophiles flourish in tough, extreme settings, even on our own planet. These creatures can be found in the cold Antarctic deserts, acidic hot springs, and the deep ocean. They make a compelling case for the viability of life under trying circumstances. For instance, Deinococcus radiodurans can tolerate high radiation levels and desiccation, while extremophilic bacteria like Thermococcus gamma-tolerans may survive in extremely high temperatures. It has been discovered that more complicated life forms, such as tardigrades, sometimes known as water bears, may survive in outer space. This shows that life can persist even in environments like space radiation and vacuum, which would normally destroy cellular structures. Because they may go into a state of cryptobiosis, tardigrades can withstand extremes of temperature from minus 273 degrees Celsius to as high as 150 degrees Celsius, as well as extreme radiation and even space. We also know that life on Earth originated in deep-sea hydrothermal vents, where the first organic molecules formed under the perfect conditions of high temperatures, intense pressure, and a lack of sunshine. Indeed, the harsh environment was, ironically, perfect for the type of life that would be virtually destroyed by it on Earth today. With their abundance of hydrogen, sulfur, and methane, these vents may have helped create basic compounds that later developed into more intricate organic molecules. We might learn more about the types of organisms that might have been the ancestors of life on Earth from the extremophiles that now inhabit the area around such vents, including Pyrococcus furiosus, which can survive at temperatures beyond 100 degrees Celsius. Therefore, even in the most hostile situations, life can find a way. Extremophilic bacteria may have adapted to the severe environment of Proxima B, giving rise to life there. Like Earth's deep-sea vents, Proxima B may offer a stable habitat for microbial life if it possesses a subsurface ocean or is shielded by a dense atmosphere. In this scenario, the warmer, more stable places might be home to life, especially those where the planet's core heat might sustain subsurface life similar to that found near Earth's hydrothermal vents. Furthermore, if Proxima B is discovered to have an atmosphere, it may have been formed by volcanic and geological processes over millions of years, which might have produced a stable environment in which life could establish itself. The planet's potential for habitability would rise if it had liquid water, because it may enable the chemical reactions required for life. It's also possible that life may live in a small, temperate zone along the border between the light and dark sides, where temperatures might be less extreme and liquid water might exist, given the planet's closeness to its star and the potential for tidal locking. Earth's extremophiles have shown how highly adaptive life is. Given that life can last in the worst conditions on Earth, it is likely that Proxima B may also sustain life provided it has the required elements, including liquid water, the appropriate chemistry, and an atmosphere. However, seeing is believing. We have only been able to admire the planet from afar thus far thanks to our observations, but eventually this dream will also come true. Space exploration's future and questions. The future has already here. We are experiencing it, or the components of it anyway. We will soon be able to send manned trips to the planet, gather samples, and get a close-up look at it. This may seem unrealistic now, but keep in mind that a species that had only learned to fly some 60 years prior made the moon landing. We're on the verge of achieving comparable successes now. For example, the Breakthrough Starshot is a long-term, ambitious initiative that will launch small, light probes to the closest star systems, such as Alpha Centauri, with the goal of transforming interstellar travel. The effort, which was started in 2016, is a partnership between the Breakthrough Initiatives, a global program that was co-founded by Facebook's Mark Zuckerberg, astrophysicist Stephen Hawking, and Russian entrepreneur Yuri Milner, among others. In a little more than 20 years, the project hopes to create probes that can reach the Alpha Centauri system at up to 15 to 20% the speed of light. Using light-powered star chips, small, flat, highly reflective spacecraft with cameras, sensors, and communication devices is the main idea behind Breakthrough Starshot. Strong lasers would propel these probes, directing enormous amounts of energy onto a light sail that is fixed to the spaceship. The star chips are propelled to amazing speeds by the lasers shining on the sail, potentially reaching velocities that are orders of magnitude faster than any spacecraft in use at the moment. This method is in contrast to conventional rocket propulsion systems, which produce thrust using actual fuel. Theoretically, light sails that harness solar or laser energy provide a far more effective form of propulsion. In the 1970s, scientists like Carl Sagan presented theoretical studies of light sails, which served as the basis for the concept of harnessing light for propulsion. The creation of the technology necessary to precisely produce and aim such strong lasers over great distances is a major obstacle for Breakthrough Starshot. In order to ensure that the energy reaches the spaceship undamaged, the laser system, which is designed to focus on hundreds of square meters of sail, must overcome obstacles such as air distortion. The harsh circumstances of spaceflight, including radiation, temperature changes, and high-velocity impacts with interstellar dust, must also be incorporated into the design of star chips. Addressing communication issues is another aspect of the entire project. The time lag between sending and receiving signals will significantly rise due to the probe's extremely fast speeds. As a result, sending data back to Earth will need creative ways to store and convey data, and most of the time, communications will be one-way, meaning that after launch, the probes will send data without getting instructions from Earth. Despite being in its early stages, Breakthrough Starshot has advanced significantly in terms of research and development. Through prototypes and experiments conducted on the ground, experts proved that light sail technology was feasible by 2021. For example, they proved the concept's technical soundness by successfully demonstrating laser propulsion capabilities using small-scale models. In order to improve the materials, design, and laser technology required for this interstellar trip, the team is also working with a number of academic institutions and industry firms. There may be significant long-term effects from Breakthrough Starshot. It might be a prelude to future expeditions investigating other stars and their possibly habitable exoplanets, in addition to enabling us to investigate Alpha Centauri and its planets. There is increasing conjecture that human expeditions could be sent to Proxima B in addition to robotic probes. Although this concept is still a ways off from becoming a reality, it is not completely unattainable. For example, NASA and commercial firms like SpaceX are actively pursuing the goal of bringing humans to the Red Planet, and the Mars mission is frequently mentioned as a first step toward human space travel. Future journeys to farther off locations, such as Proxima B, where people might be able to observe the planet's surface, atmosphere, and possibility for life directly, might be made possible if this mission is successful. Since advanced civilizations may communicate similarly to humans, the search for extraterrestrial life has historically concentrated on detecting radio waves. Proxima B, however, serves as a reminder that life can take many different forms, some of which we may not even be able to identify right away. This finding contradicts our presumptions and implies that we should look for other signs of life in addition to radio transmissions. Above all, we need to take the time and effort to go and find ourselves. This change in emphasis has the potential to greatly expand the search for extraterrestrial intelligence, or SETI. The mysteries of exoplanets like Proxima B continue to be at the forefront of astronomical research as humanity pursues its desire to explore the cosmos. These concerns may soon be addressed as scientists create increasingly complex tools, but current technology merely provides hints of the answers. An exciting opportunity to address some of these profound cosmic concerns is presented by the promise of emerging technology such as a replacement for the James Webb Space Telescope. Furthermore, Upcoming initiatives like the Square Kilometer Array, or SKA, which is expected to grow into the world's largest radio telescope, have the potential to offer hitherto unheard of insights into the cosmos. With the construction of this enormous array, which will span Australia and South Africa, astronomers will be able to conduct more thorough and precise surveys of the cosmos than ever before. SKA's extensive antenna network and unmatched sensitivity will provide groundbreaking capabilities in addressing some of the most important astronomical topics. These include how galaxies originate and change over time, how magnetic fields shape cosmic structures, and, perhaps most importantly, what dark energy is, which is still one of the biggest enigmas in physics. The field of space exploration will change dramatically as these and other upcoming initiatives develop. Astronomy is expected to have an exciting future in the coming decades, with the potential to provide answers to some of the most important concerns facing humanity. Will we discover proof of civilizations that predate us, or may we be the only species in the universe? Is Proxima B just another dead end that excites us, or will it prove to be the home of sentient life? In any event, these inquiries serve as the impetus for current space exploration and missions, directing our course into the future. Thank you for watching, and that's it for now. Was this video enjoyable to you? To ensure you don't miss our upcoming uploads, if you did, please think about liking, commenting, and clicking the subscribe button. Additionally, don't miss this very amazing video that is currently playing on your screen.